A brief history of artificial intelligence.
Few years after invention of computers, they evolved from machines with electrical switches to those performing incredible tasks like processing checks to playing checkers. This fast growth resulted in growing narrative around computers-based artificial intelligence overtaking human intelligence. However, in late 60s, the reality struck and researchers were confronted with some difficult challenges. The funding agencies around the world started cutting back on AI research, and it started losing its luster in mainstream coverage as well, entering an era that was called AI winter. During this period of slowdown, the research focus shifted towards more specific problems rather than grand goal of achieving artificial intelligence. That is basically a machine that has cognitive capabilities equal or greater of that an average human being. Let us turn our attention to some key problem categories that have been at core of AI research. Artificial intelligence problems are usually put in three categories as described by Seymour Papert: theoretical problems, toy problems, and practical problems, also called theta, tau, and rho problems. Example of theory problems can include proving mathematical theorems using AI. Toy problems often include programming computers to solve puzzles or play games like chess. Although called toy problems, these can be extremely challenging for computers in some instances. Finally, the real-world problems are those that are of most practical and commercial interest. They extend from detecting cancerous tissues, to monitoring frauds in credit cards, to translating one language into another. Two main, although not exhaustive categories of real-world problems that have been central to AI research are computer vision and natural language processing. Computer vision entails giving machines ability to see and understand visual cues like humans. This includes detecting the presence of objects, their locations, and relationships to each other. These surprisingly simple tasks for humans can be quite challenging for the computers. Natural language processing relates to computers dealing with human languages like English. The term natural language is often used to distinguish it from computer languages that are designed to be understood by the computers. NLP has four main components. Speech recognition, that involves recognizing individual sounds and words from a speech waveform received by a recording device like a microphone. An example of it would be speech-to-text converter that can create words from the speech in microphone but does not understand them. Understanding. This involves the ability to make sense of combination of words in a sentence or sentences. For instance, the sentence, "A black dog is sitting," can be parsed by the computer into a model of nouns, verbs, and adjectives like shown here. Often, whether a machine has understood a sentence can be tested by asking it a question. Next aspect of NLP is the generation of the language. This involves producing meaningful and recognizable text or speech. Virtual assistants like Siri and Alexa show example of both limited speech understanding and generation. The final category for NLP is machine translation, that involves converting one natural language to another, for instance, converting written or spoken English into Russian. NLP is one of the core problems in AI research. It closely ties to the Turing test, where a machine shall be able to communicate in a fashion indistinguishable from a human. A famous example of a machine that could give an impression of communicating with humans was ELIZA. Developed in 1960s by Joseph Weizenbaum, while ELIZA didn't understand any of the language, it could often make reasonable responses based on some set rules. Here is an example of communication with ELIZA. This response may seem reasonable, but ELIZA could easily be tricked like this. The challenge of understanding ambiguity in natural languages that is very easy for humans was extraordinarily hard for computers. For instance, consider a sentence. John saw a squirrel next to a tree. It ran away as he approached. For a human reader, it is obvious that "it" here means the squirrel and not the tree, something that is not capable of running. However, this use of common sense knowledge was and has been a struggle for computers. In the late 1970s and early 80s, those in the field were quickly realizing that AI systems might be much more efficient at replicating expert human behavior in a specific domain rather than more general human activities that require broad-based common sense knowledge, and that this endeavor might actually be more profitable. This was reinforced by development of what were called expert systems. An expert system consists of a knowledge base and an inference engine. The knowledge base contains necessary facts about a specific domain. The inference engine uses those facts to provide specific answers or make inferences. This structure indicates that by changing the knowledge base, the same model can be made useful for several different domains. A famous example of an expert system was Mycene, developed at Stanford University in the early 1970s, that brought power of expert systems to medicine with the specific goal of providing consultation related to bacterial infections and therapies. The system will ask a series of questions about the pathogen and then output most likely bacteria and a certainty factor that indicates the confidence in the result. Original version of Mycene had about 200 rules that went up to 500 by 1978. Mycene's performance was compared to that of physicians themselves. 75% of Mycene's therapy were rated as acceptable by majority of evaluators. While this may seem a low number, the agreement within physicians themselves under the same criterion was less than this. The expert systems were bringing true promise of AI that is commercially successful. Washington Post published an article on August 28, 1983 titled Profits in Artificial Intelligence that stated, "After years of hype and failed expectations, artificial intelligence is finally beginning to make some real money," and gave a thumbs up to expert systems themselves. The branch supporting the heaviest expectations is the so-called expert systems. Several companies deployed expert systems in early 80s. Digital Equipment Corp developed a system called R1 for automatic configuration of computers, an error-prone process that was costing the company millions of dollars. Around this time, AT&T Bell Labs employed an expert system called Automated Cable Expertise to support cable line maintenance. The system would do a maintenance survey in an hour that would take a week for a human. The Holy Grail was considered to be truly generic expert systems that could be applied from one industry to another. A company called Technology, a spin-off startup from Stanford University in the early 80s, claimed to have the best approach towards a generic expert system. It was generating millions of dollars with customers like Boeing in its portfolio. The list went on. Along with the excitement on the commercial side, there were important academic and funding events taking place as well. One importantly, in the land of the rising sun, Japan. 1982, Japan's Ministry of International Trade and Industry started what is called Fifth Generation Computer System Project, with a goal of developing highly sophisticated computers with a key focus on parallel and multi-CPU architectures, as well as logic programming with an aim towards artificial intelligence. The project was named Fifth Generation to differentiate it from four earlier generations of computers. At a funding of around 50 billion yen or approximately $400 million in 1990s, the goal was to accelerate Japan's research and computer industry and refute claims of those days that Japan exploits knowledge from abroad without any contributions of its own, as stated in the TRIP report from Professor Ehud Shapiro. The 10-year project is usually believed to have had mixed outcomes, but it certainly created major waves in AI development in the 1980s. On technology side, growth in parallel computing, that was one of the key focus areas of Fifth Generation project, will play a critical role in modern machine learning and AI applications. A very clear effect of Japanese efforts was an increase in funding for research in AI and related topics in the US, UK, and Europe. This was great news for researchers in these regions who had seen severe slowdown in funding for AI research. The academic research in AI had some notable developments in this period. One noteworthy work was in training of multi-layer neural networks. We had seen before that single-layer neural networks had limitations, and there were no well-accepted ways of training neural networks with many layers. In 1986, in a landmark paper, Grimelhart, Hinton, and Williams described the technique of backpropagation to train these networks. Although known in some academic circles beforehand, this publication was key in making backpropagation popular in mainstream AI research and bringing neural networks back to life. Early 80s were truly the boom times in artificial intelligence. There was growth in academic research, public and private funding, industrial applications, and also the general perception. The membership of American Association of Artificial Intelligence rocketed from 5,000 in 1980 to over 16,000 in 1987. As before, if we look at Google Ngrams, the word automation was back in popularity, and artificial intelligence was going off charts. AI was now estimated to be an industry at over $1 billion. It is interesting to note that the seasoned AI researchers warned against over-optimism and lofty promises. In fact, at AAI meeting in 1984, a discussion session was held titled The Dark Ages of AI, where moderator Drew McDermott warned, "In spite of all the commercial hustle and bustle around AI these days, there is a mood that I am sure many of you are familiar with, of deep unease among AI researchers who have been around more than the last 4 years or so. The unease is due to the worry that perhaps expectations about AI are too high and this will eventually result in a disaster." Unfortunately, although probably unsurprisingly, these warnings turned out to be true, and we will see how the term artificial intelligence almost went into shadows in the next couple of decades to follow.